Okay, you guys, so I wanted to finish up some of the problems we were talking about yesterday or in the previous class. So up here is the work we did for these problems here. And then this guy here, okay? So now I want to go, they were telling negative chance be about so now we're going to go the opposite. You guys don't have to worry about finding the answers, but I want to show you how I understood these problems, how I think about them. So it says the probability that Z, so we're here, the probability that Z is less than A is equal to 0.25. So the difference between this problem and the previous problem is in this problem, they're actually telling us the probability already, and they want to know what Z-score would have made that happen. So notice up here, this one is telling you the Z-score, and they want to know the probability of that. This one is telling you the probability and want to know what Z-score we're doing. So this is kind of going in the opposite direction. So I wrote this one over here on the side, probability that Z is less than A is equal to 0.25. So I'm going to just draw the picture for this. And again, I encourage you guys to draw the picture. It really helps so you don't feel like you're just hitting enter on the calculator. It helps you understand what's being asked of you. And they are telling us that whatever our Z value is, the area that it has is 0.25, or the area less than it is 0.25. So I think that's going to be right about here. So remember, this is 0. That means that if I shade right here, then that I'm going to have 0.25 area right here, or probably whichever way you want to think of it. And again, the point is that you think of the area under the curve and the probability of that as the same thing. So we have to find this Z value, right? Let me fix that. We have to find, oops, erased too much. We have to find this Z value right here. We don't know what it is, but we'd like to know. So what we're going to do is we're going to use our calculator function. We're going to say inverse norm. So what this does is you tell the calculator, I have an area of 0.25. I have a I have a mean of 0 and a standard deviation of 1. When you hit enter on your calculator for that, you're going to get negative 0.674. Normally we should round 3 decimal places for our Z-scores. So now remember, this is not a probability. This is a Z-score. So I have just found a Z-score that would give me that. And if you don't believe it, you could then go back up here and do one of these problems and do probability that Z is less than negative 0.67, the value that we found, 674. We could do that. And guess what we would get? We would get 25%. Okay, hold on, let me close the window. So we have our negative 0.674. We are saying this is our Z. That is our Z-score, okay? So this is the opposite of what we were doing in the previous problems. In the previous problems up here, we were finding the probability Z probability and trying to make it happen. So let's look at this other one. So this was letter A. Let's look at letter B. Says probability that Z greater than A. So it's very important, the greater than or the less than. So they're telling us the probability is 0.13. So normally you would draw this and you would say, oh, my probability of 0.13. So I'm going to go here and I would shade right here. and we'd say, oh, that's 0.13 area. The problem is we are working with greater than. So they're saying that they want the probability to be above the z value of 0.13. Well, this is technically below, okay? And when you're using the calculator always does from left to right for z-scores. So if you tell it to find area, it found the area of 0.13. So I can do this. I can do second varse inverse norm, or I'm using the distribution, and I'm going to do 0.13, and I get negative 1.126. Okay, so this number right here would have been negative 1.126. Okay, but here's the problem. What you just found was the z-score that would have 0.13 area to the left of it. But notice they want 0.13 area to the right. So what we have to do is find the score over here that would have done that. Well, because this is symmetric, we know it's the positive 1.126. So if I shade this area, I would also get 0.13, okay? Now, which one of these is correct? This is the correct answer, and this one is actually wrong, because the greater than symbol says they want the z-score. What's the probability that there's a z-score greater than whatever number we come up with? Well, we're going to come up with 1.126. If we plug 1.126 in our calculator and we do above it, we will get 1.13. Now, if you notice over here, what value did I use? I used 87. I used 0.87 or 87%. Well, the reason for that is this number right here. So this number right here, 1.126, this positive 1.126, this number right here has 87%. If I shade this area this way, there's 87% or 0.87 area this way, okay? But I don't care about the 87, I care about the 0.13, okay? Now the problem is, or I shouldn't say the problem, but the convenience of this is, well, doesn't 1.126 have 0.87 area below it? But it also then means it has 0.13. So depending on how you're looking at it, they're both technically right. If you want 87% or 0.87 below it or 0.13 above it, it's the same number would create that. So that's why we're looking right here that we could optimize the score. Use 87 and be just in case, I'll write it here. I'm going to do the probability that Z is between A and B. And it equals 0.7. I think that's what it was, right? 0.70. Okay, so here's the thing. I'm going to do my drawing again. I'm going to draw my normal curve. Okay, and I'm going to have my 0 here. Now here's the thing. They're saying that whatever this z-score is, and I believe they say centered. Yeah, they say centered. So that kind of makes it a little more convenient. So that means that this number here and this number here should be equal distance. They're centered. So we're going to say that in the middle of that, we're going to shade this region. That's what we're looking for. And that should be 0.70. Okay. So we should get 0.70, all right, for that middle area. So all I did was I took out my calculator and I said, well, if there's 0.70 in the middle, how much is missing? Well, I just do 1 minus 0.70 and I get 0.3. But remember, there's 0.3 over here and there's 0.3, a total of 0.3. So this has to be 0.15 and this has to be 0.15. Okay, so when you add all three of those directions up, we get 100% or 1, which we know has to be true for a normal curve. So I know that what if I were to use our there, inverse norm, and I'm going to use 0.15 comma 0 comma 1, and I will put this on my calculator, but actually we already have it up here. I know it's going to be negative 1.036, negative 1.036. So that means this z-score right here is negative 1.036. But because of symmetry, I also know that positive 1.036 would be this guy right here because they're symmetric. So I found my two answers, negative 1.036 and positive 1.036. Okay, so hopefully that helps you guys understand how to use the inverse norm feature on your calculator. So now what we're going to do is we're going to work with problems that do not, how do I say this, that do not use the exact z scores that we want. It's not in terms of standard normal, meaning that we're going to have to convert things to z-scores if we want to use them, and then we can later on use our calculator to even beat that. Okay, so let's see here. Actually, I think I'll jump straight into the calculator. So here we have steps to find normal proportion standardizing. Standardize the observation X with the z-score. Sketch and shade the area of interest. Find the probability of proportion using normal CDF, lower bound, upper bound. So we already know how to do this. That's what you've been practicing. So it says here, what percent of high school seniors qualify for Division II sports? So we got to read the problem. It says, the NCAA required, prior to the SAT changes, Division II athletes to score at least an 820 score on the SAT exam in order to complete their first year of college, or to compete in their first year of college. The scores of high school seniors taking SATs followed an approximately normal distribution with a mean of 1026 or 1026 and a standard deviation of 209. Well, we're going to look at this and we're going to say, well, I'm not exactly sure how to do this. So what I'm going to do is I'm going to draw my I can get 1026, and it has a standard deviation of 209. So that means when I go over this amount and this amount, I add 209. I'm going to go over more and more and add 209. So I can't do everything quite the same. So let me try to redraw this. Okay. So what I'm going to do is it says, what percent of high school seniors qualify for Division II college sports? Well, what do they need to qualify? They need a score of 820, at least 820. So what we're going to do is we're going to do the probability that Z is greater than 820, right? Because at least could be greater than or equal to, but so we want 820 or above. What students qualify for 820 and above? Well, if the middle right here is 1026, where is our 820 at? Well, that's over here somewhere. I don't know exactly where, but I know I'm going to call that 820 about. Okay. And let's see here. The athletes need to score at least an 820 on their score. So they want to know this. What is this probability? Because if you score above an 820, you still make it, right? If you score below, you're not qualified to play. So I'm going to use my normal CDF function. So normal CDF. Where am I going to start counting probability? Where, or area? Where am I going to start counting? That's right, at 820. Okay. Now, where am I going to stop counting? Well, how far will this go? You know, well, make up some really big number. I'm just going to say 9999999. You guys understand that's way over here somewhere, right? So I'm adding up area forever all the way up, but I'm just going to pick an arbitrarily large number, 9999999. So now here's the catch. Your calculator can fix this for you. Normally, when we type in mean and standard deviation, wouldn't we use 0 and 1, right? But now we're going to use the mean of this problem, which is 1026, and we're going to use the standard deviation of this problem, which is 209. So this is not standard normal, okay? So this is going to give us, let's take out our calculator. Let's do second vars, normal CDF, 820. The upper bound is 99999. And again, if you use more nines or maybe one less, I don't think it'll matter. Just as long as it's a big number, 1026 and then 209. So we get 0.8378. So this is my probability. This is my probability of what percent of high school seniors qualify for Division II college sports? About 83 to 84%, 0.8378, okay? So we have found that probability, and we never even had to convert it, and that's because our calculator does it for us, okay? Everybody okay with this? Now it says what proportion of SAT scores fall between 720 and 820. So what you do is you take your curve again, right? You draw your curve. We know that we're in the middle, and 720 is probably here, and 820 is probably here, right? And then we shade that region in, okay? So based on that, we're gonna do norm CDF of 720 to 820. What's our mean? 1026. What's our standard deviation? 209. And we're going to get second vars normal CDF of 720 to 820 and use the same 1026. And I get 0.0906 if I round off a little bit. And that would be the probability of that. So about 9% chance of an SAT score being between 720 and 820, okay? Okay, so now I just want to show you guys something. Now, if we didn't do it this way, I'm going to draw. Or, you know what, let's call it non-standard. Okay. So the non-standard method, I just did probability that Z is greater than or equal to, 820. So then I did norm, let me write this below it because I don't want to run out of room. CDF, okay, of 820, comma, 9999999, comma, 1026, comma, 209, I believe. Just check. Yeah. Okay, so we go up here, and again, we already knew the value from previously. The value was 0.8378. But now what I want to show you guys is standard normal. Okay. So standard normal says if you want, you can convert it into a z-score. See, currently that's not really a z-score, right? 820 is not a z-score. That's the problem talking. So we're going to convert it to standard normal so we can think about it as just a pure z-score, okay? So we come up here and we see this formula, z equals x minus mu over standard deviation. So I'm going to write that formula over here. So same problem, z equals mu minus, x minus mu divided by standard deviation. So that means that I'm going to have my x value of 820 minus my mean, which is 1026, divided by my standard deviation of 209, okay? So when we enter this in our calculator, we get 820 minus 1026, okay? And then we divide that by 209, okay? So we get approximately negative 0.9856. Now again, we're rounding off. So that would be my z-score. So I'm going to draw my table, or I'm going to draw my graph. Okay. Now we're back to a zero mean, and negative 9.856 would be right about here somewhere, right? So we're going to say negative 0.9856. We're going to shade above it like this, okay? And then we're going to do our calculation. We're going to do norm CDF negative 0.9856, completely different than what we were doing over here, right? Completely different than 820. This is negative 9.86, completely different value, not even close. And then we're going to go to 9999999, right? And then our standard deviation, I'm sorry, our mean is 0 and our standard deviation is 1. And let's see what we get on our calculators. So I'm going to do second vars, negative 0.9856 to 9999999, 0, 1. And I get 0.8378. Look at that. It's the same number. And that's because when you take this z-score right here, you have converted the problem into standard normal. There's also tables that we can use, and the tables, everything has to do with standard normal. So for me, I choose to use the calculator. So I like this method better, okay? And if we draw the picture, it would be the same exact picture, but instead of 0 being in the middle, we have 1026 in the middle. And this number right here would have been 820, and then we just shade. And it's literally the same drawing. We're doing the same exact thing. This one over here is in standard normal, and this one over here is in non-standard normal, okay? But they both do the same thing. They're both using normal distribution. However, when we work with this guy right here, standard normal, we normally have to do a little bit of work to get it to be a z-score first. Because we have a graphing calculator, we can use the non-standard method. So this is how things that aren't in our nice, clean z-score form, we can still work with them because we have a calculator, okay? So I just wanted to show you guys that even though up here, we use the calculator heavily to find these answers, I wanted you to know that here, we could have done it in standard normal and it would have done the exact same. We're still doing the same thing that we were doing previously, but now we're kind of leaning on the calculator to convert it for us, okay? So let's see, I'm gonna skip ahead a little bit. Let me see. Let me look at my notes, make sure we're on pace. I guess if you wanted to, we could do this. I really kind of want to skip to the IQ problem, but we can look at a safe load of water taxis was found. Yeah, I think we can look at this problem. So it says a safe load for water taxis was found to be 3,500 pounds. We also noted that the mean weight of a passenger was assumed to be 140 pounds. Assuming worst case scenario, let's assume that all of the passengers on the water taxi are adult. Passengers on the water taxi are adult men. According to the National Health and Nutrition Examination Survey, the weights of adult men are normally distributed with a mean of 172 and a standard deviation of 29. If one man is selected, what is the probability that he weighs less than 140 pounds? So just a few things to point out. Really big deal right here. They mentioned this. The moment they mentioned that, what did they just give us? They gave us normal distribution, which means now we can use our calculator with normal CDF and inverse norm or whatever they need because they mentioned it was normally distributed. Okay, so let's see here. There's no part B. I'm doing the different water taxi problem. Okay, so we know that we're going to do normal CDF and then we're going to go negative 9999999. And then where are we going to stop at? Because it says, if one man is selected, what is the probability he weighs less than 140 pounds? So if you think about it, we're doing this problem right here. So we know the mean is 172 pounds, and we know that means the man over here is 140 pounds, and we want this probability to the left. Right? So they said he's going to be 140 or less, right? Less than 140 pounds. So we're going to do up to 140. Oops, wrong color. And then we're going to use a mean of 172 and a standard deviation of 29. Okay. Let's see what we get on our calculator. So second vars, normal CDF, negative 9999999 to 140. We have a mean of 172, a standard deviation of 29, and we get 0.1349. So about, 13% chance that this could happen, okay? So again, this is kind of us abusing our calculator a little bit to do all the work for us. But really what it did is it converted it to normal. So it took a very similar situation to this. They made it normal, just like here, right? I'm sorry, standard normal. And we were able to solve it using non-standard normal. It's basically a way, kind of a workaround, since we have the technology to do it. So it makes your life a little bit easier. I would assume a long time ago, before everyone had a graphing calculator, everybody had to standardize everything because we only had the charts to work with. So you would have to standardize every single one of these problems. You would have to turn it into a z-score. And then from there, you could then use your tables or charts, okay? But for us, we're going to kind of rely on technology. So it says, write the correct distribution of IQ scores. So we have a psychologist who is designing an experiment to test the effectiveness of new training program for airport screeners. She wants to begin with a homogeneous group of subjects having IQ scores between 85 and 125. Given IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. So first things first, it says write the correct distribution for IQ scores. Well, what that just means is they're just telling you that it's approximately normal. Does it even say it in here? Oh yeah, it says not even approximately, it says normally distributed. And again, if it says approximately normal or normally distributed, we're fine with both. And they're just saying that we have 100, 15. They're just saying that we have a mean of 100 and a standard deviation of 15. When I'm not really going to test you on this, they just want you guys to know that these are the things. It's a normal distribution with a mean and a standard deviation. Those are the two most important things from the problem. So it says, what percentage of people have IQ scores between 85 and 120? So remember, all that is that's this drawing. Right? And we know that the mean of 100 is right here. And that means 85 is over here somewhere and 125 is over here somewhere. We're just kind of eyeballing it. And then we want the IQ scores in between. What's the probability of getting an I score in between 85 and 125? So we know how to do this. We do norm, CDF, and then we go from 85 to 125, comma 100, comma 15. And we should get, if we plug this in our calculator, we should get approximately 0.794. I better do it at, my notes don't have it to 4 decimal places. I got 0.79355, so 0.79, let's do this, 7936. Okay, so hopefully this is giving you guys a good heads up on where to begin. So what I'm gonna do is I'm gonna call it right now. Let's leave off right here. I'm pretty, I'm gonna have to teach in a little bit again, so I just wanted to kind of post this video for you guys. So I'm going to stop the video now, and we'll conclude the rest of this chapter in another video. Thank you.